Hello and welcome to this presentation. Over the course of it, I shall be going through question 2 of the 5 exam style questions. We begin with the information that chlorine trifluoride, hereafter referred to as ClF3, is a very strong fluorinating agent that has been used to separate uranium from the fission products in spent nuclear fuel rods. Now, this doesn't come in handy for the rest of the question, but, knowledge is power. So, yeah. Part 1 asks for the Lewis dot structure of ClF3. We'll begin by working out the total valence electrons for ClF3. ClF3 contains chlorine and fluorine. Both have 7 valence electrons per atom. Now we have 4 atoms, so if we do the calculation, we have 7 plus 3 times 21 for the fluorines, for the 3 fluorines, equals 28 total valence electrons. Now for the drawing, we'll first begin by plotting the position of the atoms in space. We'll put the 3 fluorines round a single chlorine in the middle, because the chlorine is less electronegative than the fluorines. We'll then add the bonding pair electrons, which accounts for 6 of the 28 electrons. Then we will fill in the octets on each of the atoms. We'll begin with the fluorines because they are more electronegative, and we will add 6 electrons to each one because each fluorine already has 2 electrons from the bonding pair. To the chlorine, we see that it already has 6 electrons from the 3 bonding pairs, so we will add 2 more electrons for 8 valence electrons in total. However, we find that we only have 26 electrons on this molecule, which is 2 less than the 28 we would need. So we will make use of the expanded octet rule, where chlorine being an atom with an atomic number greater than 10, we can add additional electrons as they are required to make up the number. So we add 2 to get 28, and a complete Lewis diagram for ClF3. Question 2 wants a sketch of the shape of ClF3 and a description as to why this is the case. So for this we will use something called valence shell electron group repulsion, acronymized to VSEGR or ZEGR from hereafter because it's easier to say. We'll start with a preliminary drawing, which we can see has 5 electron groups on it. Now, according to ZEGR, that means ClF3 has trigonal bipyramidal geometry. We then see that ClF3 has 3 bonding pairs and 2 lone pairs. This means it is T-shaped, with axial bond angles of just under 90 degrees and equatorial bond angles of just under 120 degrees. This arrangement also minimizes the repulsion between electron groups in the molecule. In part 3, we are asked to sketch another geometry and explain why this is not observed. On this arrangement, we see that one of the lone pairs has been moved from its equatorial position to an axial position, reducing the bond angle from 120 degrees to 90 degrees. This reduced bond angle increases the repulsion between the lone pairs, and so the repulsion within the molecule is not as well minimized as within the previous structure. Part 4 is nice and quick. It asks us for the hybridization of the chlorine at the center of ClF3. So, we know that ClF3 has trigonal bipyramidal geometry and 5 electron groups. Now only sp3d hybrid orbitals will allow for 5 electron groups. Therefore, the hybridization at Cl must be sp3d. Part 5 is the largest part of the question at 8 marks. It tells us that liquid ClF3 has a rather high electrical conductance. This is believed to be due to self-ionization of ClF3 to form ClF2+ and ClF4-. It asks that we draw Lewis structures and then name these expected structures of each of these ions. Starting with ClF2+, we will begin, as we did in part 1, by working out the number of valence electrons. So we have 1 chlorine and 2 fluorines, but the ion has a net positive charge, so we will subtract 1. So 7 plus 2 times 7, which equals 14, minus 1, will give us 20. Now we will start by plotting the positions in space with chlorine in the middle, again due to being less electronegative than fluorine. We will then add bonding pairs between the fluorine and the chlorine, counting for 4 of the 20 electrons. Then we will fill in the octets for each atom. 6 electrons to the fluorines, as they already have 2 from the bonding pairs. Then we add 4 to the chlorine to fill out its valence shell. Now, as ClF2+ is an ion, we will have to surround it with square brackets and add a plus to indicate the charge. Whilst the question only asks to name the structure, I've decided to sketch it out just for a little more clarity. We can see that the ClF2+ ion has 4 electron groups, therefore it is of tetrahedral geometry. We can then see that 2 of those groups are bonding pairs and 2 of them are lone pairs. This corresponds with the bent structure. It also possesses bond angles of 104.5 degrees. As for ClF4-, we see that we have 1 chlorine, 4 fluorines, and as the ion is of a negative charge, 1 additional electron. So that would be 7 plus 4 times 7, which is 28, plus 1, to give us 36 valence electrons. Now, when drawing the structure, we will plot the chlorine in the middle, and we will surround it with the 4 fluorines. We will then add the bonding pairs, which accounts for 8 of the electrons, so 28 to go. And then we will fill in the octets by providing each fluorine with 6 electrons, accounting for 32 of our 36 electrons. So, using expanded octet rule, we will add 4 more electrons to the chlorine to make up our 36. And of course, square brackets and negative charge. And to finish, we will work out the shape of ClF4- using Sega. We can see that ClF4- has 6 electron groups, therefore it has octahedral geometry. We also see that 4 of these groups are bonding pairs and 2 of them are lone pairs. This means that ClF4- has square planar structure, which means all its bond angles are 90 degrees. Thanks for sticking around.